Okay, welcome to the 7 steps for graphing scientific data. This is what you do once you have done standard deviation to determine what outliers you have and excluded those outliers, because we don't graph outliers. We assume that they are something went wrong there, and things that are outliers are determined through the process of standard deviation, which I've already taught you. So we now have a data set that has been checked and found to be outlier free or had the outliers excluded. So in this experiment, we measured the growth in biomass in plants compared to the amount of fertilizer they used. I will be referring to this data table as we go through. So what is step 1 in the 7-step method? By the way, you're clearly taking notes while you're watching this. Adoy. Step 1 is pretty simple, guys. You draw your axes. That's right. I am going to have you first hand make your graphs. We may not even get to how you make them digitally. Why? Because digital platforms change, but the actual understanding of how to graph data correctly never does. That's in your head. That will be with you until the day you die, and that will make you a smarter, more educated, more science literate individual. But honestly, who knows what platform will exist in 5 years to make a graph? But understanding how they're made is timeless, like classy jewelry. All right, so step 1, you draw your axes. Boom, I told you it was simple. You should have that written by now. So then what do we do in step 2? In step 2, we label the axes. Now, in math class is just your training wheels for how to graph and analyze scientific data. You have your X and your Y, right? They're always talking about X and Y in math. Why? Because they don't want to clutter your head with actual IVs and DVs and scientific interactions. Because they're just like, we're going to teach you the basic math. We scientists have to understand at least the basics of math and all of the science. So, in reality, the x-axis, that is where your independent variable goes. Goes. And the y-axis, that is where your dependent variable goes. So as a reminder, this is my data set. You want to determine what is the IV and what is the DV. As a reminder, the IV is the thing that you think is the cause. It's what you are changing up to test. The DV is the thing that is going to be affected by the suspected cause. So between our two options, we have growth in biomass and the amount of fertilizer. If we think about it, the only possible one that could be a cause of the other is the amount of fertilizer. By changing that, we will cause potentially a change in the growth in biomass, making that our DV. So I come back here and amount of fertilizer goes on that axis, and on this axis we put the DV, growth in biomass. And that's it. That's step 2. Moving on to step number 3. This is also very simple. In step number 3, you just add units to the axes labels you just created. So, and you put those units in parentheses. So I'm going to come back to the data table. Oh, because I already figured this out, I know that my fertilizer is in grams, and I measured my biomass in milligrams. So I come back here. I put parentheses after the title, and I include the unit that they were measured in, grams, and this one was milligrams. That is critical because data numbers are largely meaningless unless we know what unit it is in. Without units, we just have relative relationships, but science isn't just about relative relationships, it's about discrete ones, meaning we need the units. All right, so that is step 3. Step 1, draw the axes. Step 2, label the axes. Step 3, add units to those labels, which brings me to step 4. In step 4, you need to create your scale. Now, your scale are the numbers that you put on the axes. The scales for the two axes do not have to match, but the scale for both your X and a Y should meet 2 criteria, and I will be deducting points if they don't meet both criteria. Number 1, your scale must be even. By that I mean each number on the scale has to have the same interval. This is what I have seen before, right? Let's say we're graphing the mean. So 7.1, 7.2, and 10.6. I have had so many students look at those numbers and say, okay, 7.1, 7.2, and 10.6. And that is my scale done. No! Bad job. Bad student. Because from 7.1 to 7.2 is a difference of only 0.1. So then to have my next interval go all the way up to 10.6 is incredibly wrong. If I was going by tenths, then my next interval would need to be 7.3. And if I go to 7.3, I can't fit all my data in. So that does not work. So instead, I need to go by each number I put has a even interval between them. So if I go by ones, it's 1, 2, 3, 4. If I go by tens, it's 10, 20, 30, 40, 50, 60. If I go by 0.2s, it's 0, 0.2, 0.4, 0.6, 0.8, etc., etc. Now, the second criteria your scale must meet is it must be appropriate. Now, what does it mean to be appropriate? That means all the data that you have fits between the low and the high end of your scale without there being too much excess space in your graph. I'm going to demonstrate a bad example of this. Again, let's now go with the amount of fertilizers, that 0, 5, 15. If I go 0, 5, 10, obviously that is a inappropriate scale because I cannot fit in my 15. Okay, so then what if I went by tens? 0, 10, 20, 30. That is, okay, cool, I can fit my data in, but the problem is I only need to go up to 15. So half of my graph is going to be empty. So that's an inappropriate scale because it's just too big. So I do need to go to just above 15 because I can't go to just 15 because you can't have the highest number in your graph be the end of the scale. So what I'm going to do is I'm going to go to 16 and I'm going to go by twos. 2, 4, 6, 8, 10, 12, 14. Boom, there we go. I wish I had some graph paper, but that's fine. Those would have been much more even if I had. All right, and so for my biomass scale, where I'm going to go from 7 to 10.6, I could do a couple things. I could go from 0, so I could move my 0 to the corner here because now it's the 0 for both. And I could go 0, 5, 10, 15. That works. I could also leave that as 0 and go 5, 6, 7, and 8. Because that would, actually no, I couldn't because that wouldn't include all my growth. Whoops, bad Barker. I could go 5, 10, 15. I could do that. In fact, that is what I'm going to do. So those are my scales. And that's create a scale. That's step 4. All right. We are now moving on to step 5. Remember, we're more than halfway through this method right now. Okay, so here I am back again with the graph as I currently have it designed. And now step 5 is go ahead and add that title. Why do we do that now? Why isn't that step 7, Miss Barker? Because I've been teaching for almost 20 years. And when I had step 7 as write the title, guess what step every student forgot to do? Write a title. So I've moved it earlier in the 7 steps. The title will go across the top, and you can simply use the format effect of IV on DV, making this effect of amount of fertilizer, and I'm going to include in grams, on growth in biomass in milligrams. And there's my title. And that's step 5. Again, just use the format effective IV on DV. So you're literally just plugging in whatever you labeled the IV and whatever you labeled the DV. This is why we do this after we set up the scale and the axes, but before the last step so that we do not forget to do it. Which then brings me to step 6. Now, step 6 is actually, you don't always have to do it, but sometimes you do. You may have to make a key, but only if you have multiple IVs. So for example, let's say my data wasn't just testing the effect of fertilizer, but it was also testing the effect of water. Then I would need 2 different lines, 2 different colors. Here I have a dotted and a solid, but when I look at this data table, I have amount of fertilizer and I have biomass, and that's my DV, so I only have 1 IV. That's the only thing I changed as the scientist. So I do not need to do this step for this data table, but there are some of you who are designing projects that have multiple independent variables, which is great. In that case, you will need to use a key. Which then brings me to step 7. So we have axes, labels, units in those labels, even and appropriate scale, title, and I don't need a key, but if I did, it would be there. That means it gets me to step 7. I'm going to graph the data. Now, scatter plots, that's those things that look like this. Those have a lot of uses. And as I've been telling you, when you're doing real scientific research, a math expert is going to weigh in and tell you, hey, this is the best way to, this is probably best to do a scatter plot. It's probably best to do a histogram here, blah, 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 blah. For me, I am your PI. I am telling you that you do scatter plots for individual groups. So like you would have a scatter plot that showed all of the trials for your 0 grams. You'd have a scatter plot that showed the 5 grams. You'd have a scatter plot for the 15. But when it comes to line graphs, for me, as your PI, your primary investigator, if you are graphing the average, meaning we are actually comparing the groups, which is what we need to do to draw conclusions, you're going to graph only the mean, and you're going to do that as a line graph. So let me see if I can juxtaposition these. Juxtaposition means put side by side. Okay, so my 0 grams, my mean is 7.1. So I come here and I find the intersect. Now, I have a lot of students who don't know how to do this because of graphing calculators doing it for them. So finding the intersect means I go to my independent variable, which in this case is the 0, and I go to the dependent variable and I find where they intersect. So 0 is obviously right here. So I'm going to take this paper and I'm going to lay it there. And then I'm going up to 7.1, which is going to be about right there. And that's it. The intersect is where the 2 points meet. My next point is 5 grams and 7.2 milligrams of growth. So now I'm going to find the 5, which is right there. So I'm going to lay that there. I do have students who do this. You can do this if you want to as like a setup, but I don't want the lines, so I'm going to erase these. And then 7.2, which is going to be right there in terms of milligrams of growth. So my next point would be there. To be clear, I have had some people tell me their math teacher wants them to do those lines, and I understand why. It makes it easier for them to grade that you have graphed it correctly. But those lines sloppy up the graph, which then makes it harder for us to look at the trend. As your science teacher, we care about the trend and the correlation between the IV and the DV. Is this IV having an effect on this DV? And if so, what? So I don't want those lines. But you're welcome to use them if you would like to. And then my final data point was 15 grams of fertilizer and 10.6 grams of biomass. So 15 is here. So I'm going to come up from the 15. And 10.6 would be about right there, just above the 10. So there is my final data point. And then I draw my curve. In a line graph, you do connect the points. In a scatter plot, you draw the line of best fit. So you draw the appropriate line for what that is. And kiddos, that's a perfect graph. That's a perfect scientific graph. So here's what I can conclude from this. Hey, from here to here, there's not that much change. So my conclusion, which I'm just going to write across the graph, is that this fertilizer increases biomass growth only above 5 grams dosage. Now, that's not super helpful. I don't know. I mean, I guess I could say the 15 gram dosage is best, but because there's almost no difference between the 0 and the 5, I guess I could also say that 5 grams does not change the growth in biomass compared to the negative control, which is the normal, which was the 0 grams of fertilizer. So if you are going to use this fertilizer, you want to use more than 5 grams because 5 grams won't do anything. And those are the conclusions we can draw from that scientific research. But mainly, I'm going to erase this. Please don't write your conclusions in your graph. Oh God, I've just thought of that someone's going to stop this video and be like, oh, I wrote my conclusions in the graph. Don't write your conclusions in the graph. I just did that for the video. Okay, thank you very much. You have now learned how to correctly scientifically graph data. And if you can do this correctly, you are smarter than the average American. See you in class.